Assalamu alaikum. Welcome back to School of Physics, Understand Universe. Today, in this lecture, we will discuss, as you can see, the Newtonian physics and classical physics, or we can say classical mechanics. So earlier, before that, we have dealt with the fundamental forces and force in general, I can say. So now onwards we will discuss a kind of physics which deals with the microscopic world, especially more specifically with the microscopic world as well, but its domain, the physics which comes under the category of the Newtonian physics, its domain is actually the microscopic one, because in the microscopic, in the smaller world, in the small physical world, these laws which are given by the Newton, they actually fail. So we will be mainly dealing with the we can say the microscopic world, the physics of bigger world, the physics of bigger things. Earlier we discussed various topics, as you might, if you are already on my school or my channel, you might be well aware about the things like force, the fundamental forces. We have already discussed all kind of these things earlier. As we know, there are four kind of fundamental forces, in the universe, which are actually the gravitational force, and there is electromagnetic force. Then comes our nuclear forces, which are of two kinds, or that are the strong nuclear force and the weak nuclear force. Now today onwards, we will be specifically dealing with that portion of the physics which deals with the microscopic world, which comes under the category of the classical physics, which was actually in we can say fully understood on the basis of we can say on the physical level, which was made understood by Newton. Actually, he was the founding father of the modern physics. Actually, before him, it was Galileo who actually made the foundation of this classical physics, but the actual work which was done in detail, it was Newton actually. So that's why he is referred to as the father of the modern physics, we can say. Although actually Galileo is treated as the father of modern physics, because Newton himself laid the foundation based upon the laws which was given by the Galileo Galilei. So that's why we can say the founding father of the modern physics is Galileo. So now onwards, you have to keep in mind that we will be dealing with the classical world, not the quantum, not the general relativity, not that stuff. Keep that very stuff aside. We will be dealing with those very concepts in the later lectures. So today onwards, for few lectures which are upcoming, we will be dealing with the classical mechanics. As you might be already known about the forces in the nature, which I have discussed earlier. Now, to keep anything, say for example, there is a body, say body A. To keep this body in motion, we know we need a force, because force is that very agent which causes any body in an motion. So there are two types of motion, we can say. For just understanding, we have motion means the moving bodies, we can see the moment, or the body which changes the position with respect to time, I can say. Okay, so any body which changes its position with respect to time is said to be in motion, and that very motion, the body which is set in motion, is actually the working agent behind that very motion is actually the force. Okay, so we have two kinds of motion here. we can say the uniform motion, and another thing we have non-uniform motion. And the causing agent behind both these is actually the force, but there is a major difference. This uniform motion here, the working agent we can say is force on the first place, but it is not compulsory that any body which is moving does need a force, because if a body is moving already, it no longer needs force. It will keep on moving. Okay, this is actually demonstrated by Galileo. We will talk to that in a bit later time. So actually the uniform motion is said to be that very motion in which velocity is kept constant. So it deals with that very bodies which are possessing some velocity, and the velocity is not changing, no change in the velocity. So those very bodies in which the body is moving, but the velocity is not changing with time. So velocity is constant. So that very motion is called as the uniform. And in contrast, the bodies which have not a fixed velocity, those are said to be in non-uniform motion. So that means actually those bodies are having or possessing the acceleration. Okay, so that means accelerated bodies possess the non-uniform motion. Okay, so there are two types of motion. One is uniform, in which the velocity is kept constant. For example, this body, it's on the first place. If it is given the force will change its state. Okay, for example, it's at rest, it will come into motion. But as long as force is kept aside, we are not now applying the force upon the body, it will start moving with a uniform motion. And that uniform motion, if no change in its velocity takes place, that is said to be in the uniform motion. Similarly, if we continuously push this body, say Fa is first applied, then force B is applied, then force C is applied, that means we are continuously changing its velocity, we are continuously changing its state of motion. Okay, so that means the body is not possessing a uniform velocity or uniform motion. That means the body is possessing the accelerated motion, that is the non-uniform motion. Okay, but there comes a problem. For example, say we set this body here, a body A is there. We have to, now there was a problem in the early ages at the time of Aristotle. What they were thinking before Newton and before Galileo, there was a problem that there is a body. If it is set in motion, then do we need an external force to keep this very body in uniform motion? So there was a query, we can say there was a question. The question was, is an external force required to keep a body in uniform motion? For non-uniform motion, we know that if the body is accelerated, so there must be a force behind that. It is well understood. The body must possess acceleration, possessing acceleration must be governed by some force. So that is well understood, that we need a force to make a body accelerated. Okay, but in case of the uniform motion, there was a question at the time of Aristotle. He tried to answer it, that is an external force required to keep a body in moving, to keep a body in uniform motion. Say a body here, if it is applied force and it moves with a velocity, say v, and at some, say, time t, at time t plus 5 seconds, it is also possessing the same velocity, v. Aristotle was the first who tried to answer it. That is the Aristotelian theory of motion. So we will discuss that, whether we need external force to keep a body in uniform motion, because uniform here, you know that now. Acceleration here, no acceleration is possessed by the body. If it is moving with the velocity, if it's moving with a uniform motion, with a uniform velocity, that means there was a question that whether force is required behind that. Okay, but Aristotle, he tried to answer it. We'll figure out what he tried. For example, now we will discuss the Aristotle's theory. Okay, it was actually a fallacy. Keep that in mind. He tried to answer it, but the theory he gave was completely incorrect. He tried to answer this very question. He said that suppose we have a ground, and over it a ball is laid down. We apply force onto this ball, say a body A. It will be displaced by some distance, okay? But it's a common observation, it's a common sense that with respect to time, at some instant of time, it will come to rest. So velocity will be 0. So Aristotle thought that there is some kind of tiredness. This body gets tired. This body gets tired as the time passes, okay? So he thought that, like the human beings, if they work with respect to time, with the passage of time, human body or human beings, they need a rest. They come into rest because they are tired. And similarly, all the objects in the universe, in the physical world, they come to rest because they get tired. It was Aristotelian view, and it was common observation, and at that time it was well known, and it was famous among all the thinkers of the physical world which were dealing with these kind of stuff, okay? We can say physics. But this was a fallacy. He said that the bodies, like human beings, they get tired. So he suggested that every body, if a body is kept in motion, if we want to keep a body in motion, to keep a body in motion, what kind of motion? It's uniform motion. The fallacy comes here, the uniform motion, because I already told you that if the body is in non-uniform motion, then certainly we need a force behind that, because to change velocity we need a push, we need a pull, we need some external agency, which is the force here, to keep accelerating. But in case of the uniform motion, the velocity is kept constant. Aristotle said that as the body gets tired, so we need external force. To keep a body in motion, we need an external force to keep the body moving on, okay? So Aristotle gave the theory that an external force is required for every body to keep that body in uniform motion, but that was wrong, completely rejected. That's the Aristotelian fallacy. Look what the fallacy is. This is a fallacy, okay? It was proved that this is a fallacy because now, today, we know that it's completely wrong. Aristotle completely ignored what we today call that the frictional force, what we call that friction. So it was well established for many years, many centuries, I can say, that Aristotle's theory was completely right, because as we know that if any body is set in motion with respect to time at any instant of time, it comes to a halt, it comes to rest. But it was not because that it is tired, that's why it comes to rest. But the theory, the first person who proved that this is actually a fallacy, it was Galileo Galilei, the founding father of modern physics. Galileo Galilei. What he did, he did some experimentations over this very problem to solve this. He took an object like Aristotle took, but on an inclined plane. This is an inclined plane. A body is set here, okay? He set this body free, and we know under the effect of the gravity, every body which is at some inclination, or at some height, it comes down. Similar effect happens to this very object. This comes down, and he observed that at the initial point, its velocity here, the velocity was 0. But as this body is set free, it comes in motion, and here it comes in acceleration. So velocity changes from 0 to some velocity, say v. Say v is 10 meters per second, okay? So there is a change in the velocity, and we know the change in the velocity is called as acceleration. Keep that in mind. Acceleration is change in the velocity with respect to time, okay? Or we can represent it for shorter periods of time, for shorter instant of time. It is represented as dv by dt. This is the acceleration. You might be well aware about this relation. So he observed that if the body is set free, it comes in acceleration. Okay, it is accelerated. He did another experiment. In this case, inclination was reversed. He put a body here, okay, at this point. We know it can't climb uphill of its own. We need a push for that. He applied some force onto it, starting with velocity 0. He tried to push it, and it's got at the first instant of time when force is applied, that is at t is equal to 0, its velocity is v. When it is set in motion, before that it was in rest. When force is applied, it comes in motion with a uniform velocity at the first instant. I'm saying at the first instant of time, the velocity is v. Okay, but as it climbs upwards, its velocity gets down, gets decreased. Okay, velocity gets decreased, and it reaches some point. At this point, velocity ultimately dies. Velocity comes to 0. Okay, then he concluded that the body is retarded, because first the velocity was some, say, 10 meters per second, but ultimately it dies out. So there was a kind of retardation which is opposite to the acceleration. So here retardation was observed. The body got retardation. Okay, 2 experiments. One where acceleration is brought into existence. Another experiment, here retardation was observed. Then with the same force, he applied onto an object on a plane which is horizontal. Okay, he applied same force, so the initial velocity here was velocity v. Say for example, here it traveled the distance of 2 meters. Here, say for instance, 2 meters same. But here, when he applied the force here, same force with the same velocity moving first at the first instant, he observed that with the passage of time, as it covers 2 meters, the body does not stop here as in the first case. it goes on, and stops here. Why it stops here? There was a real reason behind that, but it doesn't stop here at the 2 meters per second, at the 2 meter distance, which earlier was the case, earlier, okay? It stopped later on in the after time is equal to say 60 seconds. Fine, traveling a distance of say 50 meters. So he observed that, he concluded that it was not the body which gets tired, because same body was here, same body was here, same body was here. Okay, at the first instant, same body got accelerated. In the second case, it got retarded. So if the body gets tired itself, so why in the first place, why on the first case it get accelerated? Because it is getting more and more energy, as per the Aristotle theory, if it is considered to be true. It should have retarded in this case also, in this case also, and in this case also. But only here retardation is observed fast, okay? So he concluded that there are 3 types of motions. One is acceleration, which is the accelerated bodies, observed in the accelerated bodies. Second one is retarded bodies. And third one is intermediate, okay? Intermediate. He further tried. He did another experiment. Furthermore, he took a bowl-shaped container and took the same ball here at some height h from the ground level. This is the ground level at some height h. Okay, he dropped it, but now onwards he kept in mind that this body, the container, is smooth surfaced. That is, he got an idea that the main reason behind that is not the tiredness of the object. It is something dealt with the surface, because here the surface was of one kind, here the surface was of another kind. Here the surface was of another kind. So he took in consideration the nature of the surface. So for that, what he did, he made the smooth surface as much as possible. So he did an experiment. He dropped this down. It was possessing some velocity. It came here, and ultimately it came almost to the same height. Although there was a difference in height, but approximately we can say this is up to the same height, because he tried to smoothen the surface as much as possible. It is not 100% smooth, frictionless, 100%, no way. So that's why I'm saying that it was approximately h. Say it is h. So he further did the experiment with the same ball, but now he made the surface of the bowl like this, stretched, a kind of stretching in the bowl, but at the same height. The ball was again dropped with the same velocity v. Okay, he observed that as far as this surface is smooth, the ball reaches the same height again. Wow, that's a kind of craziness now. This was a jerk to the Aristotelian theory. If the distance is stretched here it was only this much of distance to cover by the body, but here it is almost the double. Okay, he stretched the distance and observed that almost the same height is observed here also. Same height, but distance right now is double. So he concluded that with the passage of time, if we do the experiment, say we do the experiment, so this very portion is kept is lowered right now onwards. He did another experiment. He put a surface like this on the first place. On one side it was at some height, but on the another side he tilted it down. Okay, like what I am trying to say, like he made a bowl, he made a container of this shape like this. So he dropped it down with the same height h. Okay, with the same height h, with the same velocity it is dropping down again. and when it dropped down with the same velocity, he concluded that as much as he tried to smoothen the surface, smooth surface, almost frictionless, because this was the main reason behind all that experimentations which were coming, which were actually falsifying the concept of Aristotle. Frictionless, almost, okay? So when he dropped it down, he observed that the ball continuously moving, okay? And he concluded that if we are able to make the surface frictionless, this was the main reason, frictionless, the keyword in here, it is the frictionless, then what he concluded, then the body will be in uniform motion forever. That is, it can travel a distance of infinite. This was the, I can say, this was a jerk and blow to the Aristotelian theory. So the main key factor here was the frictionless surface. For example, take the same bowl. If it is surface is rough, that's with very much higher friction. At the first instant, velocity is v, but as it goes down, it comes under the effect of the friction, and frictional force pulls it down, so retards it. So the maximum travel distance is this. But as the surface is made frictionless, smooth, and is dropped at some height h, it tries to cover the same distance. So Galilei, he suggested and he proposed a theory that it is all dependent upon the friction of the surface. As much as we lessen the frictional force of the friction of this surface, the body keeps on moving. Okay, so for frictionless condition, the body can move up to the infinite distances. So that means we need not to possess, we need not to, we can say, exert some external force. We need no external force. We need no external force for a body to keep it in uniform motion. To keep it in uniform motion. That was the main statement of Galileo Galilei's theory. He said that no external force is required. A body keeps in moving with the uniform velocity as far as the surface is frictionless. So to keep a body in, suppose in the ideal situations, because in the day-to-day life we come across the friction, okay? Suppose the surface is frictionless. Galileo Galilei supposed that for any body to keep in, if a body is moving with some velocity, that is the uniform motion, that will continue to move in the space-time forever, and no external force is required for that. So we got an idea that the body with uniform motion does not require any external force. So this was an insight. So this was an insight given, which was given by the Galileo Galilei, that had eluded Aristotle actually and his followers. He concluded that uniform motion what Galileo Galilei did. Galileo Galilei. What he concluded: uniform motion is if it is contained by some body F, it does not require any external force. So that means it will continue to be in the uniform motion. Similar case happens with the body which is at rest. Suppose this body is at rest. If no external force is there, this body will stay at rest, will remain at rest forever. So Galileo Galilei said that uniform motion of a body is equivalent to saying that it is equivalent to the state of rest. Is equivalent to say that it is equal to the state of rest. That means in both the cases, if we want to change the uniform motion of a body, we need force to change it. We need a force to change it. That means, or for similar situation happens to the similar case happens with the rest state. If a body is at rest, we need some external force to change it. Okay. So what he concluded that if we have, I will write it down, if net external force is 0, that means no acceleration will be observed, that is, no external force will be there. A body at rest continues to remain at rest, Similarly, and a body in uniform motion continues to remain in its state, okay? Continues to move with uniform motion, okay? With uniform velocity, I can say. So he concluded that if a body is at rest, it will remain forever until and unless compelled by some force. And if a body is in uniform motion, that means it is possessing some velocity, it will remain in the state of motion moving with the uniform velocity until and unless external force is applied to it. So it will resist any external change. So no change will be happening inside the body until and unless some external force is applied to it. So this state possessing this process, this property is called as the inertia. So inertia, we can say this is a resistance to change. Resistance to any change. For example, the body is at rest, it will remain at rest. It will try to resist it to change its state. For example, it's at rest, it will remain at rest. Similarly, the body is in motion, uniform motion, it will remain in the uniform motion, it will resist the outer changes. That property which is possessed by bodies, this property is called as inertia. And Galileo Galilei said that he gave a law, actually. This is called the Galileo's law of inertia. Galileo's law of inertia. That any body continues to remain in motion continues to be in its original, continues to remain or to be in its original state. Fine. So this was the Galileo's law of inertia. That's if a body is in motion, uniform motion, it tries to remain always in the uniform motion. If it is at rest, it tries to remain at rest until and unless external force is applied to it to change it. Okay, so this was the founding base of modern Newton's laws of motion. This, which I said, the law of inertia, this was the founding base of Newton's laws of motion, and it is sometimes it is also referred to as Newton's first law. So we will discuss here Newton's first law. So that's why Galileo is treated as the father of modern. That's why Galileo is treated as the father of modern physics, because the founding base of Newton's laws was the Galileo, Newton's laws of motion. Newton's laws of motion. What was the first law? There were three laws actually: first law, second law, and third law. You might be well aware about those very laws, but I will give a brief concept about those very laws. So first law, which is also called as the law of inertia, first law of motion. First law of motion says that every body, I will write it down like this: every body continues to be in its state of rest, one thing, or of uniform motion, These are the two things. But according to Galileo, these two things, rest and uniform motion, these are equivalent to each other. Not in that case that rest is equal to the motion. No, that's not the case. He said that as long as external force is not applied, both of these conditions are not changed. So this also needs to change the state of rest. It also needs force, external force, and uniform motion. This also needs some external force. So the first law of motion, Newton quoted that every body continues to be in a state of rest or of uniform motion along a straight line, or in a straight line. In a straight line, because straight line motion is possessing the uniform motion. Straight line. Then in that case, or of uniform motion along a straight line, unless compelled by some external force, to act otherwise. For example, if the body is at rest, then if external force is applied to it, if it is first at rest, okay, if external force is applied to it, it will come in motion with some velocity v. So its state is changed. First, it will possess the property of inertia. It will remain at rest. Now, since the external force is applied to it, it will possess some velocity. So its velocity changed from 0 to v, and change in the velocity is called as the acceleration. Okay, so force brings in acceleration. This is the key word for the second law of motion. Keep that also in mind. Okay, similarly, if the body is moving with some velocity v, here it is also v, but here applying force, if force is applied in this direction, or say in this direction, opposite to the velocity of the motion. Okay, so in that case, first it was moving with the velocity of v, but here it comes to rest. So velocity comes to halt, that's v equal to 0. So velocity is again changed from v to 0. So that means again acceleration, in this case it's retardation, so that means again the acceleration is observed, whether in the negative direction or the positive direction. That is the case here, it is the case of retardation. So acceleration is again observed. So this acceleration is again caused by some external force. Okay, so that means Newton said that every body, it continues to remain in the velocity in the uniform motion. It continues to remain in the at a state of rest until and unless some external force here is acted onto it to act otherwise. Okay, this is the only condition that a body can change its state, and this was totally opposite to that for that theory which was given by Aristotle. Aristotle said that no, to keep this body in uniform motion we need an external force. Newton said, Galileo said that no, you are wrong. It is external force required to change the uniform motion, not to keep the body in uniform motion. If external body, the body comes to which you think, they said to Aristotle that you think that the bodies are tired. It's not the bodies becoming the something like human beings. No, it's actually the ground which is providing the friction. Okay, so it is this very frictional force which is making the bodies to come in rest. So here external force acts as the friction acts as the external force. Okay, so first the body was moving with the uniform motion, then the friction force is applied to it, it comes to rest. It is not the body is getting tired, no. Similarly, if the body is at rest, to keep this body in motion, we need some external force. In all the cases, whether the body is at rest or of uniform motion, to change the inertia of this very body, we need some external force. Okay, this was the first law. So every body tries to remain in its state, original state, unless and until compelled by some other external force to act otherwise. This was the Newton's first law. So we said that the acceleration here is caused by some external force. So we can say that, but there is a problem. Suppose a body here, if a force is acted onto it like this, it will come, for example, it's at rest, it will come in motion. But if another same force is acted in the opposite direction, one force is acting, F1 is like this, F2 is like this, and both cancel out each other, what will be the end result? This body will stay in the state of rest, because both of these forces are cancelling out each other. Fine. So that means if the total sum of the external forces, say for example here another force is acted onto it, here another, this cancels out this cancels out this, another force like this, another force like this, these two cancel, another force like this, but here another force is like this cancels this very thing. So that means the sum of the total external forces, that is the resultant net external forces, resultant are the net external forces. If net external forces onto a body is 0, they are cancelling out each other. Similarly, in case of the moving bodies, if the total forces acting onto the bodies are cancelling out each other, that is the net resultant force is external force, I am saying, is 0. That means there will be no change in its original state. That means no acceleration will be brought in. Okay, you saw here that acceleration is brought in by what? By some external force. But here force is applied, but forces are cancelling out each other. That is the net acceleration, net external force is 0. That means if a body is observing a net force of 0, external force 0, that means there will be no acceleration. Or in other words, if a body is not accelerated, if a body is not accelerated at all, if it is moving in a uniform motion with a uniform velocity, that means there will be no acceleration, and that in turn means that no external force is acting onto it. Or this is equivalent to saying that the total forces, if there are more than one force, two forces, more than two forces, then the resultant of those very forces is actually 0. Because it is as if the total forces are acting onto it. It is as if that no force is acting onto this body. So that's because no acceleration is observed onto this. Like I can elaborate this very concept in another example. I will give another example to you. For example, say here is a table, okay, and we are keeping a book onto it. This is a book onto this, okay. Now I'm saying to you, is this book at rest or moving? Clearly it's at rest. It is at rest. That is, we know from the first law of motion there must be the acceleration is what? Acceleration is 0. That means the external force must be 0. For here, we know what kind of forces are acting onto it. Like we see here, no force is acting. But in reality, this body has got mass m, okay. So downward, always there is a gravity downwards, so the weight of the body is downwards. Weight of the body is, for example, this pen. If it is possessing a mass m, there is always a gravitational force downwards exerted by, I discussed it earlier also in the fundamental forces, the gravitation. So gravitational force will be acting downwards. Okay, here will be the gravitational force like mg. So there is an external force, but since we are observing 0 acceleration, that means this force is counterparted by some another force, and in this case it is upwards force. So this book, which is here, it is acted upon by two forces, mg, that is the weight of the body, which is the downward force, the force of acceleration, and it is counterparted by some external by another force, which is called as the normal force. And the normal force is caused due to the contact between two bodies. Here that means the table and the book itself. So there comes another force, that is the normal force, which cancels out the downward gravitational force. So the net result is n plus mg is 0. That means n must be the opposite to mg. So acceleration due to gravity, which is causing the gravitational force, is opposite to that of the normal force. So in this case, we saw that the body will remain at rest because the net force is 0. So there will be no acceleration in the body. This is given by the first law. Similarly, you might have heard about if we are in a bus. For example, this is a bus, and it's moving with the velocity, something velocity, and we are standing in this bus. If the driver here applies brakes suddenly, so this comes at halt, this comes stop, the bus is stopped suddenly, we feel what? Forward jerk. Why? It is because the property of inertia inside our body. Our body was first moving with the velocity, with the same velocity with the bus, with the bus was moving. So our body tries to remain in what? Uniform velocity. But now our feet are in contact with the bus, exerting some force, and the frictional force is exerted onto our feet. So our feet are at the instant time when the brakes are applied, our feet come to rest with the bus, but the upper part is not. It is still in moving with velocity. So that means our upper body part, our upper body will feel a forward jerk. Similarly, when the bus is at first, if it is set in motion, we will feel a backward jerk. That is because of the property of the law of inertia, okay? Because our body possesses inertia and our body tries to remain in its original position. So that's all for today. I hope you got this idea. These are the basic concepts in the physics. So in the next time, I will deal with the momentum and other kind of stuff. So this was all about the first law of motion. I hope you got it. Kindly support and cooperate. I will see you in the next.